Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. We're not going to waste any time tonight, so let's get to it. Alright, I don't think we're making any headway on this particular problem. We were working on it on Monday. No, Sunday. And yeah, it was going pretty much nowhere. So kept kind of going around in circles a bit. I need to maybe do some work offline and figure something out. In terms of how to, it's a lot of work. In terms of how to figure out how RDN is exactly 1/7 the area of SGO, the big one. So, gotta still work on that a bit. We'll figure it out later. For right this second, we're going to pull up the calendar. For anybody who is not aware, this is the September 2011 edition of Mathematics Teacher from NCTM, National Council for Teachers of Mathematics. And they released a particular calendar for October, which was basically do a problem a day, and then like you could show your students, you could do basically anything you want. So we've gone through the first 9 problems, I think 10 problems without too much trouble, and number 11 was the one that was giving us some trouble here. Oops, where are we? There we go. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. So number 11's a bit of trouble. And we'll move on to number 12. See if we can't find something a little bit easier to work with. Alright, 3 similar rectangles with integral widths and lengths in ratio 1 to 2 form a non-convex hexagon as shown. I think. Pretty close. Not quite. Alright, something like that. Width of the largest rectangle is 3. Find the hexagon's perimeter. So if they are in a 2-to-1 ratio, then our long side of the small one's going to be 6. That also means that this is going to be split up into 2 different pieces, probably 2 and 1, since they are integral. This one's going to be 2, and this one's going to be 4, which aligns with the picture. Okay, so the overall hexagon is going to have side lengths. Okay, it's going to be 2 there. Okay, so, sum of the digits of the hexagon's perimeter. There we go. Alright, so 18, 20, 21, 22, 23, 26. 2 plus 6 is going to be 8. And so number 12 here is going to have a value of 8 filling in the circle. It's down in this corner. And again, we know that that should be the case because our magic squares are always going to add up to 15 in a 3x3 magic square. Cool. Well, that wasn't too hard. Alright, 13. The equation. x squared plus px plus q is equal to 0, where q is not 0, has two unequal roots such that the squares of the roots are the same as the two roots. Okay. The squares of the roots are the same as the roots. Okay, so that's an interesting question. Is that going to be that, give me 1 second. Okay. So if the squares of the roots are equal to the roots themselves, does that mean that p squared is equal to... That doesn't make any sense. P squared is equal to p, right? That can't be right. The squares of the roots are the same as the two roots. But does that mean that p squared is equal to q and q squared is equal to p? And it said they have to be different. So it can't be 1, which would be the easy answer. Oh, wait, no. Sorry. No, the roots. There we go. Those are not the roots. Okay. So, x is equal to negative p plus or minus square root p squared minus 4 times 1 times q, all divided by (2a), which is just 2 in this case. It's not like the sum of the roots or anything like that either. So what is going on exactly? I think I did this last time and I may have done it incorrectly. So that also makes it interesting. Right, their product has to be an integer. P and Q's product has to be an integer. Oh. That might be too easy. The square of the root, x squared, is going to be the same as the two roots. So that should mean that here this is going to be, this is just going to be x in both cases. And then that would mean that these two things can combine to make p plus 1 times x is equal to negative q. we don't have to go through all the process necessarily of solving this, but there should only be two solutions that we actually want in this particular case. I'm just going to say 2x is equal to negative p plus or minus square root p squared minus 4q. 2x plus p. Now we can square both sides. It's going to be equal to p squared minus 4q. This is going to be p squared plus a 4xp plus 4x squared. Nope, okay. So if we use the fact from above, this stuff is just going to turn into that one. So we don't want that. Right, we've already got it. Oh, whoops, there's a p squared on the other side too. But then that and that can go away. And then is it just the same thing? Yeah, it's just the same thing. I shouldn't be surprised. Might have gone too far. Might have gone too far. Ah! Uh-oh. Redo? Uh-oh. The Y, right? Control Y should be doing redo. Okay. Oh well, we got manually, I guess. So the product of P and Q. I don't have any particular occasion to multiply P and Q together. Right, there's no way to like add stuff over, multiply things. I mean, I could, in theory, multiply both sides by either P or Q and then get it in terms of everything else. But I need a number specifically. And allegedly this is all the information I need. So we'll see how that goes. Okay, one more time. The equation has two unreal roots such that the squares of the roots are the same as the two roots. So the squares of the roots, x squared, is going to be the same as the roots, x. Whichever version it is. It doesn't matter. It's going to get you the same thing. Okay, calculate the product P times Q. Okay, so hypothetically, we take this over here and make it P times P plus 1 times X is equal to negative PQ. Right, that's what we want. So PQ is going to be equal to a negative P plus 1 times X. And then, right. get the feeling it should not be this hard. So I'm going about this in a much more roundabout way that's going to take forever, I'm sure. Okay, so 0 is equal to... I should have done it here. Alright, this is going to be xp squared plus xp plus pq. Didn't know if making this a quadratic in P might help for some reason, but no, it doesn't look like it either. And I do know what the answer should be, because again, we know that it's a magic square, and we know the other two values in that row slash column. Right, so we know the 9 and the 5, so it should be a 1. Right, should be a 1. Again, the two roots should be distinct from each other, so we shouldn't just get 1 and 1. That's not what it's asking either, because, right, the roots are unequal. P and Q can both be 1 for that matter. All right. This may be just going way too far. Alright, so if we put negative q over p plus 1 in for this x here, then we're probably going to end up with just, again, all the same stuff. Haven't actually tried it, so sure, why not? X is equal to negative q over p plus 1, which is then equal to all this stuff, negative p plus or minus square root p squared minus 4q all over 2. Negative 2q is then equal to p plus 1 times negative p plus or minus square root p squared minus 4q. And again, is that going to get us anything? Interesting question. And as always, if anybody has any questions, feel free to drop them in the chat. And we will address them as soon as we are able. If I'm just faffing around with stuff like this, then we're going to go for it and take whatever you got. Alright, p squared minus 1p is going to be equal to p plus 1 plus or minus p plus 1 square root of p squared minus 4q. That's interesting. Why did that q turn into a p? Oops. That one. Minus 2q. This is now going to be p squared plus p minus 2q. Alright. Get the feeling simplifying stuff will lead us back to where we started in the first place again. Yes, right. So don't do that. Well, we can just see what's going to happen here. So if we square both sides, we end up with this nasty trinomial squared and trinomial. Those of you who don't know me, right? This channel works with stuff that is usually called the Pascal triangle. In higher dimensions, this is going to be an nth dimensional simplex. In this particular case, it's a third dimensional simplex because we have 3 items that we would like to then expand outward. So in this particular case, we also want to square it. So we're on the 0, 1, 2 second row. So a 3-dimensional simplex will, generally speaking, look like this. Where we're going to find the central point of all these individual rows. As we go down, the 1 is for what happens when we take a plus b plus c and raise it to the 0th power. So you get 1. When you have a plus b plus c to the first power, you get 1a plus 1b plus 1c. So that's where our 1, 1, 1 comes from. Our a plus b plus c squared is going to end up being a squared plus b squared plus c squared plus 2ab plus 2bc plus 2ac. Super brain! How you been? Oh yeah. So I'm just centering all of the individual points and saying like, okay, this is going to drop straight into that. Oh, you can't see that one. This is going to drop straight into that, which is going to drop straight into that. basically at every time that we drop one layer, you have 3 options to determine where we're going. So you're going to fall through, essentially, man, I got to get my picture from over here. You'd think I would have done it by now, but, you know, eh. Drive. New folder. Call it stream or streaming stuff. I don't know. Streaming assets. There we go. And let's actually pull this stuff up. Imagine that. All right, pictures. Nope. Man. Yeah, it's been such a long time since I've been over here at all. Let's see. E drive. No, Twitch. Big thing that says Twitch on it. Yeah, that would help. There we go. All assets. Audio clips. Screens for scenes. Thumbnails. Yes, I think that would do it. And then we're going to drag this all over to Drive. A. And who has access to this? Effing nobody. Me, and only me. All right, cool. Okay. So yeah, the reason that I bring this up is that I have had this for a super long time. One of my friends drew it up for me. Such an awesome thing. Oh, really? You didn't actually... Okay. It didn't... Okay, now I'm really confused because I added a new folder. That was called Streaming Assets. And I told you to put all this stuff in it. What the hell? Oh, okay. Jeez. Huh. Error estimator for small circles on a sphere. How small are we talking? Because if it's like less than 1/1000th of the radius, there's a good chance that it can just be estimated as if it were a sphere on a, as if it were a circle on a plane. But if we're talking like GeoGuessr or something like that, yeah. So you can find a, you can go ahead if you want. You could try to find like what's the arc length along the sphere, in which case it again simplifies to a arc length of a circle. So you can make it just a cut, two-dimensional cut of the three-dimensional sphere. So you're trying to find something very specific. Yeah, if it's a great circle, then it just ends up becoming the circle, with radius the same as the radius of the sphere. But you're talking about not on the surface of the sphere. That could be an interesting one. Sorry, I keep returning to this. Yeah, I mean, it just ends up being the, right, it's the angle times the radius. It's going to get you just the, okay, so yeah, not what you're talking about then. Scene 04, be right back. Actually, this should be like OOA, be right back. And we're gonna take this, we're gonna copy it. Sorry, I'm still here, I promise. I should have literally just hit copy. That's too bad. Alright, got a startup. Ah, there we go. Duplicate. No, this is OOA. Hang on. Alright, kill the one for be right back. Remove. My face. Alright, startup, duplicate. It's going to be 00A. Be right back. Okay, and then instead of startup GIF, or whatever, this is going to be, oh, instead image. This is going to be called BRB. Okay, and then we're going to take pictures, Twitch, scenes, BRB. Hey. We'll clean that up someday. Okay. Anyway. Ultimate Goal is a gradient descent type program that moves spheres of interest in such a way that it's a projection onto a panorama sphere closely matches a circle on that panorama. So are you... Is this literally projecting something on the interior of a sphere? Or is it figuratively projecting something on the interior of a sphere? Okay, anyway. So if we square this, this could be p to the fourth plus 2p cubed plus right, 1 p squared minus 2p squared q minus 2p q. Wait. No, it's just still right. PQ plus 4q squared. 1, 2, 3, 4, 5, 6. Cool. Projecting one sphere onto the surface of a panorama sphere as seen from the center of the panorama sphere where the camera of the panorama was. Alright. So a little bit like not observatory. The thing where you project the... Oh, man. Come on, what am I thinking? Planetarium. A little bit like a planetarium. Science museum or something like that. Gradient descent program. Okay. So gradient descent is your neural networks. We're trying to figure out how to get the sphere of interest. So you're essentially saying, like, how close are we? What's she doing back online, man? That was somebody who streamed earlier. Squared times p squared This is a pretty big mess. Yep. But good news, this will eliminate some stuff. So here we have p squared is going to be multiplied by all the terms in p plus 1 parentheses squared. So that's going to be p squared p to the 4th plus 2p times p squared. This is going to get me back to the original statement, isn't it? Oh, I know this all too well. I've played this game many times. Plus 2p cubed. Yeah. Plus p squared. Okay. Minus 4 p squared q. Minus 8 p q minus 4q. That's it. Yep. Alright, p to the 4th, 2p cubed, p squared. Squared q. So if we add this to the other side, we're going to get 2 p squared q. There are 8 pq's here and minus 2 there once we move them. It's positive 8. So it's going to be plus 6 pq. And then here we have a 4q squared. On the right, that is a minus 4q. Interesting. Okay. 4q squared plus 4q. Whole family of valid spheres from small sphere up close to huge sphere far away. Yep, fair. So we need multiple panoramas to do an SFM-esque reconstruction of the scene. That's why I can't just calculate it directly. You need the estimator. Oops, that was using those. Whoops. Let's just go like this. Grab all of nope. Grab all these, and then say that was totally there the whole time. I don't know what you're talking about, officer. Gotta watch out for the math police. And just as a reminder, we have developed an awesome math community in the last month. I've been poking around on several of their channels already anyway, but we were like, hey, so we should probably like officially make some sort of group or something. And so this is our or something. I'm currently using Enigma bot, so thank you Enigma very much for helping out. And just to see if yep, Penn Center we've been hanging around with a bunch. E to the 2I Pi has been in here. And I was like, oh yeah, thanks for coming, guys. This is great. And they're like, yeah, we're educators too. I was like, wait, what? Obi over here thinking he's monopolizing the industry. Yep, so Zach from E to the 2I Pi and Penn Center have been in here a whole bunch over the past however long. And Ian Stuckey, Danny Highway, and Dawn Does Math were like recently added to my sphere of perception. I had no idea who they were, and then it was like, hey, wake up. Time slot, yeah. That's interesting, because Zach should be live right now. Blainland. Round robin with quantum, huh? Okay, so round robin is something that I knew from game shows, where basically if you have like a team event, round robin is like during question 1, it's going to be person number 1. Question 2 is going to be person number 2. Question 3 is going to be person number 3, and it just keeps cycling the whole time. So in this particular case, doing stuff with round robin scheduling is exactly the same. So you're going to say that I want task number 1 to be assigned slot 1, task number 2 to be assigned slot 2, etc. And it splits up the time equally or unequally if you decide to program it a certain way. You could allow it to be like, you know, I want this particular schedule to be followed. Round robin in its truest sense means that everything gets an equal shot. So it's going to have an equal amount of processing time until either the process is done or it's out of CPU time, at which point it resets and goes to, or not resets, but it goes to the next process. With quantum, so it's looking like when you just say quantum, it's like the same thing. It's just quantum computing's version of allowed CPU time. Whatever you want to call it. So how many quanta is it going to go through, I guess, or something? So it's looking like you could do the same thing for network packet scheduling. something multi-threading. Have you been here the last few days? Because that sounded suspiciously similar to my response. So turnaround time is just the amount of time it's taken for a process to be returned. So like from when it arrived to when it got returned, from when it got sent back. So, for instance, your turnaround time on writing this homework assignment is most likely going to be like 1 class day or 2 class days, something like that. sure, your teacher will accept at most 1 or 2 class days for turnaround time. Better yet, Shark. Good evening. You wrote a scheduler based on round robin back in college. Yep. Would not recommend. Nah, it's I mean, it's going to be a pretty common response when I don't know what the hell I'm talking about. So, but I think that's pretty much anybody too. Let's see. Okay, cool. Yeah. Okay, so everything's got at least 1 Q. Hooray. Q is not 0. That was given in the question. So we can divide out by Q. Jerks. Alright, which is going to end up getting us 2p squared plus 2. Let's divide by 2q. Yeah, I don't think it's going to actually be the exact same thing I had before, but it's going to boil down to one of the previous statements, I think. It won't be quite as obvious. 3p. There's a 3 there. I don't think I've had a 3 before, so that's good. Plus 4q plus 4 is equal to 0. Okay. This is actually doable. Q could be equal to, this is going to be negative p plus 3. Okay. That'd be a quadratic. According to this, they're not going to be both be 1. So that's interesting. Cool. Sudoku grid in 2D. Check column. Loop through with a single for loop. Yeah, if you just want to check a row or a column, then you can do a single for loop. If you wanted to check each row and column, then yeah, you probably get nested for loops or whiles, I guess, if you want to do that. Q isn't even positive. Yeah, I guess. They don't have to be. But P could also be negative. Just as equally likely. I don't know about using threads. Yeah, I guess if you're doing multi-threading, you could have 1 thread for each column. Sounds reasonable. Let's treat this as a quadratic. So P is going to be equal to negative B is going to be negative 3 plus or minus the square root of B squared is 9 minus 4 times A is 1. C is 4Q plus 4. Yep. So it definitely has to. Or I guess it could be fractional. Proportional to n grid. I mean, if what you have is a Sudoku square, right, then like if you want to check the whole thing, right, it's n squared time. So I'm not sure, that's not true. No, it's 2n. Because you only have to... okay, 3n. Because you have to check rows, you have to check columns, and you have to check squares. But it's only literally, in a 3x3 grid, it's only 9 rows, 9 columns, and 9 squares. Oh, it is n squared. Right, yeah. I mean, I don't know how you want to check modulus. I guess you want to check, make sure that each number is represented and exactly once, but at the same time, like, why would you need to check modulus? You could just check it against a list. Yeah, one thing I did want to bring up is that Zach, e to the 2i pi, is currently, I think, running a real analysis class. So if anybody has thought, hey, I'd like to take real analysis, like, now's a good time. Oh, there he is. Yep, okay. I was getting worried it was, like, not showing up on there. It's so weird. If it's a 4x4, you sum 1, 2, 3, 4 equals 10. Make sure there's no duplicates. Okay, so if you want to sum up any integers, right, you want to get... yeah, I guess. N plus parentheses, 2 parentheses, n minus 2. Not quite. We'll do that next. So, -3 plus or minus square root of, this is negative 7 minus 16q. Yeah. All over 2. Yes. Most definitely a fixed series formula. So anytime that you want to do like adding up any number of numbers, that's the one. Yep, you got it. Right, Gauss figured this one out. He wasn't the original person, but he... Righto then. All right, there we go. So, I mean, if you want any square, it's just that same thing, right? It's up to n number of numbers. You can then take your n minus 1, n minus 2, all the way down through, in this case, the last two numbers here, 2 and 1. If we were to sum up all of these things, then we end up with n plus 1, n plus 1, n plus 1, oops, not n, n plus, what? So here, the number of numbers we have in each of these rows here is just counting. It's 1, 2, 3, 4, all the way through n. So we got n plus 1s, but we used two series 1 through n in order to get this, so we have to divide by 2 to get the full sum of the integers from 1 to n. Yeah. Overall sum of all the cells of an n by n Sudoku grid should be n times the triangular number of n. Recursive maze. Oh, my colad's maze. Column or each row should sum to that triangular number, and there are n of them. Okay, that's fair. Pierre Simeon de la Place? Or which Simon do you mean? I don't think I know who that is. Cracking the cryptic? I don't know that syntax. If the grid row column equals 1 dot return, invalid. Yeah, so the calendar math is back this way. We were working on this one. The x squared plus px plus q is equal to 0 is a quadratic equation whose unequal roots, so non-repeated roots, have squares which are the same as the two roots. So that at least got us that x squared was going to be equal to x here. And then when we combine x plus px, that's going to be p plus 1 times x is equal to negative q. Which then has taken us on a bunch of random turns and weird things. So we do have... I could just go back here, I mean, honestly, and check, like, a few numbers. The roots x of this particular thing are going to be that negative q over p plus 1 has to be an integer. It doesn't technically say that. So, like, I don't know. Like I said, it's taken us on quite a wild quest here to go find what this is going to be. So now we've gotten down to a new quadratic here and said, okay, 4q plus 4 is going to be our c, and then it got us down to here. So again, p and q have this particular relationship. We can't use any of the prior relationships to talk about this, because if we do, it's going to collapse into a tautology. At least I'm pretty sure it is. P is equal to negative 3 plus or minus square root. Alright, 7 plus... No. Don't do that. Alright, 16 negative q minus 7 all over 2. So we know, for instance, that q has to be less than this whole thing, right? Negative 7 minus 16q has to be greater than or equal to 0. And in fact, since we know it's non-repeating zeros, it has to be greater than, strictly greater than 0. It's going to be negative 7 is greater than 16q. So q is less than negative 7/16. Or negative q is strictly greater than positive 7/16. So so we do know that 13, like the answer that we're going to put into this grid, has to be an integer, because it has to be the solution to a 3x3 or a square in a 3x3 magic square. And because it's a magic square, we do know that its value, which is the product of p and q, must equal 1. So they are multiplicative inverses of each other. in some way, shape, or form. If they could be just 1 and 1, but I think that's going to be boring. Nope, wouldn't be. Interesting. If Q was 1, or -1, I guess, then it would make this 9. Square root is 3. You'll get -3 plus 3, which is 0, and -3 minus 3, which is going to be -6 over 2. If P is 0, then we multiply 0 times Q1, or -1, and we get 0. Or we multiply together, -6 over 2 is going to be -3 times -1 is 3. But we know that that's not the answer, because again, it's supposed to be the solution to a magic square. And again, it should have a value of 1. So if we put in different values, we do want the values to end up with a with an integer overall, and we're probably not anyway, going to get roots for either P or Q, because that'd be really awkward to plug into here. So at the very least, P and Q are going to be rational. So if Q was a half, for example, that's 8 minus 7 is going to be 1. If Q's a half, we get a square root of 1 is 1. -3 plus 1 is going to be -2 over 2 is -1. And Q would have had to be negative a half. So then their product is negative a half. Or product is a half. So that's not going to work. If Q is negative a half and we use the negative version, it's going to be -3 minus, there we go. Right, let Q equal negative a half. We end up with the square root of 16 times negative half minus 7. Ugh. Oh, wrong one. Okay, square root of 8 minus 7. -3 all over 2. It's going to be -3 plus or minus root 1 over 2. Again, this is going to be -4 over 2. So P is going to be -2, while Q is equal to -1/2. So PQ equals 1. Woo! Oh, goodness. All right, verified. All right, that last one should be 6, I think. 13 plus, yep. Okay, 9 and 6 makes 15. Diagonally, 9 and 6 makes 15. And column, 9 and 6 makes 15. Cool. So this last one should be a 6. in this section. Number 14. Rectangular sheet of paper 2 by X inches, where X is greater than 2, is cut into 3 congruent pieces by 2 straight cuts, as shown below. So, rectangular piece of paper, 2 inches, X inches, cut here and here into 3 congruent pieces. Find the area in square inches of the original rectangle. 2x. Done. All right. So okay, where x is greater than 2, so, right. Oh, no, that's right. Rectangular sheet, 2 inches by x inches, where x is greater than 2. Yeah, okay. So all of this is x. Okay, we're good. Okay, that's going to mean that all these y's, because they're congruent, are all just going to be 1. So this is not very difficult. So this is going to be 2. It's going to be 1 is 3, and x is 3. Find the area. It is going to be 6 square inches. So, verified. Okay. Number 15. In a trapezoid. CPHL. With, nope. Very much wrong. Okay, with median OU. Something like that. Nope, other way. Cup hole. Uh-huh, nice. I was right. Sometimes it just works out. CL is equal to 20 inches, and PHP, whatever, is 12 inches. Of the many line segments in this figure, which one must have a length of 4? Okay, so let's look up the definition of median of a trapezoid, because I gotta make sure that I have this right. I think that means that all the stuff above and below have to be the same length. You know, the two sides have to be split into median of a trapezoid. Line connecting the two legs at midpoints. Yes. Right. Now, they don't have to be the same as each other. So they could be at any sort of angle, and if they're like this, they're definitely not going to be the same length. So PU and UC are the same, and HO and OL are the same. The length of the median is always the average length of the two bases, which also makes sense because if we're talking about, right, CL is 20, PH is 12, UO equals, they're 8 apart, so it's 16. It's going to be the median of both of those things. Yeah, Braylon, I'm sorry, I can't. I won't be able to figure that one out. Right, so these all have to have, well, we know that, right, the side lengths are going to double. Compared to the original, compared to the big one, CPHL. They're not similar to each other. It's just that, right, they're not similar to each other. It's just that that exists proportionally. Okay, so all of our lengths with CU and UP, LO and OH are going to be proportional as if we were looking at this as two lines that would continue like this for a while, right? And then we get two big triangles. Alright, so like PL and CH are way too big to be 4. That's not going to be a problem. Okay, so like I'm pretty sure I know what the answer is, and I don't want to be too obvious about it, but if we extend it out to a point where we get 3 triangles, these 3 triangles have to be similar to one another by, right, trapezoids have to have certainly the top and the bottom are going to be the same. But then the middle one is going to also be in the same direction. So that's going to get us our 3. That's going to get us our 3 similar triangles. If I call that thing way up here like Z, right? This is going to be PZH, UZO, and CZL are going to all be similar triangles. Which is not necessarily going to get us anything good, but it's worth something. Maybe. Okay, so this means that PH to UO is going to be equal to PZ to UZ. pH is going to be 12 over 16 is going to be 3/4. PZ is, I don't know, let's just call it X divided by don't know that one either, huh? X plus PU. It's at least got a name. I mean, you know, X still has a name. It's PZ, but I don't know. I just I thought it'd be a little different. I don't know. Whatever. It's fine. Okay, and then also pH to UO is going to be equal to, no, not UO. I just did UO. pH to CL. Might actually be better. It may actually be better to do the other one. PU to UC. So instead of pH, let's do UO to CL. Okay. If it's UO to CL, then the two lines that are corresponding on the left, let's go with, are going to be UZ to CZ. Remember, these are proportional as triangles, not as trapezoids. So that's going to say that UZ is going to be UP plus PZ. CZ is going to be that's not it, man. No, that's right. Okay. PC is the top part, UP is the inside there. Okay, so UC is the same as PU, UP. So this is going to be 2 UP plus PZ. That's going to be equal on this side. UO is 16 and CL is 20. Divide by 4 and we get 4/5. Okay, so we've got two systems of equations, or a system of equations. I hope this will work. We can multiply this over. It's going to be 3 PZ plus 3 PU. It's going to be equal to 4 PZ. And 4 makes this 8 UP plus 4 PZ. It's going to be equal to 5 UP plus 5 PZ. Subtract 5. And subtract 4 PZ. 3 UP is equal to 1 PZ. And also, on the other side, subtract 3 PZ. Yeah, cool. It's the exact same thing. PZ is equal to 3 UP. Alright. PZ is equal to 3 UP. So the whole length is going to be 5. We knew that anyway. If anybody has any ideas here, feel free. Backseating mathematics. Woo! Alright, I'm going to remind myself in about 10 minutes we're going to take a 3-minute ad break, go get some water, cycle it out, and take dishes back and things like that, because I got a lot of dishes in here now. After our real analysis stream earlier on Zach's channel, just didn't take things out of here. Whoops. I think we might be able to come up with something for like our diagonals or other side lengths, but it's just really not working for us. Because everything I'm getting could be applied equally to the other side. So for instance, I'm pretty sure HZ is then going to be found to be triple HO. So that's all the same. Alright, probably gonna have to come back to that one too. Again, I know what the answer should be. Getting to that point is going to be kind of important. Alright. 16. Second half of the month. October. Close enough. Find all integral values of x such that 2 to the 2x squared minus 9x plus 4 is equal to 5 raised to the x squared minus x minus 12. Alright, easiest thing to do, take natural log of both sides. Two x squared minus 9x plus 4 is equal to natural log 2 times all that. It's going to be equal to the natural log of 5 times x squared minus x minus 12. It's the actual find all integral values of x such that this is true. Okay. All right. In those 3 minutes, I'll be right back. And we're back. All right. Thanks for sticking around and supporting the stream. If you have any questions, please let me know. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We are getting back into more mathy type stuff. Right now we're trying to find integral solutions, which will get us these two things. So the easiest one is going to be if they share any zeros. So again, easiest solution is if they share zeros. So that's going to be 2x squared minus 9x plus 4, are they going to be equal to x squared minus x minus 12? Well, hang on. Equal to 0, equal to the other one. So, do we have any of those? So this is going to be, so 8, same sign, both negative. This is going to be, nope, don't do that. This is going to be 2x squared minus 8x minus 1x plus 4. It's going to get us a 2x factored out, leaving behind x minus 4. This is going to be a negative 1, leaving behind x minus 4. This is going to be 2x minus 1, x minus 4. Okay, this is going to be x squared minus x minus 12, opposite signs, bigger one's negative. They have to be factors of 12, so 4 and 3 are off by 1. So x minus 4, x plus 3. If we multiply it out again, it's going to be x squared plus 3x minus 4x is minus 1x. Negative 4 times 3 is negative 12. Cool. So yes, they do. X equals 4 is going to be one possible solution. It is quite possibly the only integral solution. Wouldn't surprise me. Another way to check this is if we go on to like Desmos and try and plot solutions. That might just be easier here. I don't know. When it starts having, you know, quadratics in the exponent, that's when it kind of becomes a lot harder. 2 to the x squared, no, 2x squared. Minus, not. Minus 9x. Plus 4, right? 2x squared minus 9x plus 4. 2x squared minus 9x plus 4. Yep. And 5 raised to the power of... x squared minus x minus 12. Cool, cool, cool. So 4 comma 1 appears to be the only solution at all. Yep. Right, red is floating above it here. And then it's going to have higher values. Sorry, the blue one's going to have higher values at every point beyond that. At least I think so. Yes, because if we factor out a 2 from the 2 to the 2x squared, if we factor out a 2, it's going to make it 2 squared is 4, raised to the x squared and a bunch of other stuff. But the important part is going to be that first bit. So, right, 5 to the x squared. This is going to be 2 to the 2x squared makes it 4 to the x squared. And granted, the other stuff's cut in half now, but doesn't much matter. Yeah. Doesn't much matter. All right. And if we want, we can also check Wolfram, just to be sure. 2 raised to the... Uh-oh. Oh no. What did you do? 2 raised to the 2x squared minus 9x plus 4 is equal to 5 to the x squared minus x minus 12. Not only the only integer solution, it should be the only solution at all. Actually, you know what? The negative one, there might be, yeah, there's probably a negative value that's going to be the same. Or that's going to be also a solution. Approximate form. Cool. So yeah, negative 24 point something. There are also two complex solutions, and then integer solution of 4. Alright, cool. Right there. 4 comma 1. Given that this one over here is 1 times 10 to the 194th and all sorts of stuff. It's ridiculous. So yeah, in this particular case, that's the only possible solution. X equals 4. Oops. I hit something. Okay, so 15. 3, 4, 7, 11, 15. That's not 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I marked the wrong one then. What is this? That's 16. Okay, cool. I was going to say there's not a text entry on that one, so. That's 16. Repeating decimal 0.3333, etc. in base 10 is the fraction 1/3. The same repeating decimal in base 9 can be written in reduced form as a over b, where a and b are in base 10. Find the sum of a plus b. Alright, so... over 3 in base 10 is equal to 0.333 repeated, which is equal to what in base 9? Okay, so we're in this particular case, right? We're taking 3, we're trying to divide it into 1. Right? And so in base 10, we're saying that here we're taking 3 divided into 10 is going to go 3 times. But it doesn't go into 1. It's going to go in 3 times, but then that's only equal to 9. So when we subtract that off, there is a remainder of 1 which comes back up. Right, and yeah, we can mark up here, or we can continue this long division thing out that way. But I prefer actually doing this like shorthand. So it's 10 again, you get 3 with 1 left over. You get 3 with 1 left over, you get 3 with 1 left over, etc. So 3 in 2, oh no, it's not 3 necessarily. Right. That's not what I want. I want that one. Get rid of it. In base 9, we want something that goes in 0 times. And then again, is just going to keep having the same remainder over and over and over again. It's going to go in 3 times. So in base 9, what has a remainder of, what subtraction has a remainder of whatever this thing is? Well, 1's going to be the easiest if we do 3, but that's not base 9, it's base 10. Damn it. Alright, so let's do 1 over 3 base 9, I guess. See what happens. No. So 1 over... Okay. So 1 over 3 in base 9 is just going to be super simple because that's 1, 9. Divided by 3 is just going to be 3. Or... No. It's 0. Hang on. It's going to go in 0 times because it's still 1, right? Base 9. Right, 3 into 1.000 whatever is going to be okay. 1 is going to be 0, but 3 into base 9, 1 0 is 9. So that's going to get 3, and then it's a terminated decimal. So it's going to just stop there. Okay, so 1/3 base 9 is just 0.3. Which means it has to be I don't do enough work in alternate bases. So if it was like, I don't know, 3/4 base 9, and we're saying that we're taking, I'm doing all this like off the screen. This is not helpful. Okay, so if we do 3/4 base 9, then what we're going to want to do right, 4ths, nope, base 9. Jeez, that does it. Right, 4 does not go into 3. Point. 4 goes into, this is 3 9s, so that's 27. All right, 3 0 in base 9 is 27 base 10. So that's going to go in 6 times. And 6 times 4 is 24, which leaves a remainder of 3. Ooh. Which then is going to be 6s all the way down. Right, returns a remainder of 3, and then that's going to be, again, 4 divides into 3 0 base 9, which is again 27, 6 times, which gets us 24 base 10. Subtract that from 27 base 10, We get 3. Continue. Okay, that's going to work. I'm converting everything to base 10 because I'm awful at this. But let's see. 2/4 or just even a half, right? Is it even a half? Is it the same as 1/2 in this one, in base 9? Okay, so 2.000 goes in 0 times. 4 goes into 18. Right, 4 times. With 2 remaining. So it's going to be 4s all the way down. Okay. So how does 1/2 work? Is it the same? Oops, 2. 2 into 1 goes 0 times. 2 into 1, 0 goes 4 times. With 1 left over is also going to be a 4. Okay. So it simplifies to the same value as it normally would. That's good. What's 1/4? So 4 goes into, this is 9, right? Once. This is 0, sorry. 4 goes into 9 twice. And then we're going to have 1 left over. So it's 8 out of 9, leaves 1. I mean, in theory, I'm just making sure. Thank you, I'm sure. How's it going? My name is Obi-Wan Pez. This is NCTM Pachinko. We do all sorts of fun math stuff on Tuesday nights. I should technically have only just gotten home from a karate class, but my back is not having fun this week, so we decided to pass, not exacerbate the condition. Although, I think it may have been the lumbar support in my chair, which was actually making it worse. So I removed that, and we'll see how things go. So what we want is 0.333 repeated. In theory, right? 3/8. 3/8 base 9. Right? It's going to be 8 into 3 goes none. 8 into 27 is going to go 3 times. Hey, there we go. And then that leaves 3 to get to 27, which drops this over here, which makes that a 3, which then, etc. Yeah. Okay, cool. So it's 3/8. And again, halfway between a quarter and a half, right? I can spell. Man. Yeah. All right. Cool. So that's going to get us 3/8. It's A over B. Yeah, okay. No, that's cool. We can do that. That's allowed. Number 17 should be A plus B is 11. So this is a math calendar that was given out by the National Council for Teachers of Mathematics in September 2011. And I thought it would be fun to do the one a day thing kind of like all at once. Um, so we just finished up the 17th one. I'm still trying to figure out, I know what the answer is, but like why, right? How are these things the answer? So we verified this one. Have yet to verify these two. And in my shame, it'll sit there for months, I'm sure. Okay. 18. The expression x to the 4th. This is fine. The expression x to the 4th plus 11x cubed plus 30x squared plus 53x minus 7 will factor into two non-factorable quadratics with integral coefficients. Find the sum of all of the coefficients of those quadratics. Okay. So if we want rational solutions, which don't necessarily have to be correct, it doesn't have to be rational solutions, but, or rational coefficients, or rational quadratics, or anything for that matter. But we can try it at least and see if it does come up with something slightly convenient. Okay, this is going to be factors of 7 plus or minus 1 and 7 over the factors of 1, the leading coefficient. So we'd like to try a 1 and 7, positive or negative, and figure out if those are going to be at all any solutions to this quartic. If it is, great. If not, oh well. It did say oh no, it says non-factorable quadratics, right? Hey. Yeah, non-factorable quadratics. Alright, never mind. Right, because it can't be rational if that's going to be the case. I'm not going to see the pattern here. We're not going to get a 1, 11 something out of the last 3 terms. So that's not going to be it. It's quadratics, so it's not going to be skip terms. We're not going to get, like, you know, the 4th term, the square term, and then the linear term aren't going to be plug in some numbers for the coefficients, multiply it out, see what the relationships need to be. Yeah, that might be the case, I guess. Or just generally speaking, right? We could do it as x squared plus bx plus c times, nope, d x squared plus ex plus f, right? So a plus d x to the 4th plus cube is going to be AE plus BD x cubed. X squared could be AF BE CD. This is going to be pretty ugly here, but yeah. Oh, yep, that. Man. Probably. C times that one gets the x squared 2. Are there any others, right? No. Just getting paranoid, it's fine. X squared. Okay, plus linear is going to be our b plus f. Oops. No, b times f. Wow. B times f. And c times e. Plus c times f. Okay, so c and f is going to make that at least fairly easy, due to the fact that that's going to just be 7 and 1. One of them's positive, one of them's negative. E plus B is going to be 11. BF plus CE is going to be 53. It's kind of big. F plus BE plus C is going to be 30. 1, 2, 3, 4. 1, 2, 3, 4. Alrighty. We can do this as B, C, D, E, F. Oh, it's 5 unknowns. Oh no, we don't have a D. Never mind. B, C, E, F. It's not linear. Never mind. Oh, so wish. It's going to try to do that as system of equations, but not so much. All right, we'll open some of this up and make sure that that works. Yeah, thanks, Sensation. Yeah, we're trying to pop out some relationships that are going to exist for this particular thing. So okay, so without loss of generality, x squared plus bx plus 7 first. Okay, x squared plus ex minus 1. right? If E and B make 11, then let's see what happens when we do like 6 and 5, right? So in this particular case, we end up with B times -1, so that's -6 and 35. It's going to be 29. That is X. So that's not quite close enough there. It means that those numbers need to be a lot bigger. So if we went, oh, okay, 7 and 4 might work. What if we did 7 here, 4 there? No, it's 49 and -4, which gets us 45. Again, closer. 8 and 3, 56 minus 3. Yep. Okay, that's looking promising. 30 is going to be from F, so -1, plus BE is 24 is 23, plus C is 7 is 30. Excellent. All right. So with it being as it is, right, this is going to be 1 plus 3 plus 7 is going to be 11, plus 1 plus 8 minus 1 is just going to be 8. So that's going to be 11 and 8 is 19. Well, that doesn't work. Let's read that question again. Integral coefficients, all right, got that. Find the sum of all coefficients of the quadratics. Right, 1x squared plus 3x plus 7 multiplied by 1x squared plus 8x minus 1. Multiply it all out, we end up with x to the 4th plus 8x cubed plus 3x cubed. Okay. Plus 7x squared minus 1x squared plus 3 times 8 is 24x squared. Right, 24 and 7 makes 31 minus 1 is 30x squared. Sounds good to me. All right, linear. This is going to be a 7 times 8, so 56x minus 3x gets us 53x. And then 7 times -1 gets us -7. Seems right. So 1 plus 3 plus 7 plus 1 plus 8 minus 1. That's going to go away with that. This gets us 15, and 4 is 19. But I can't get 19. Find the sum of all the coefficients of the quadratics. All right. Reason being, this needs to be a 4 by 4 magic square. so it only goes up to 16. And it did say integral coefficient, so it's not like it's, you know, half on one and 2 on the other. X to the fourth plus 11x cubed plus 30x squared plus 53x minus 7. I mean, I copied it right, so that's good. You know what? Let's do orange there because that's not supposed to happen. Okay, 19. Figure that out eventually. Find the value of k such that the graphs of the lines defined by the 3 equations given below are concurrent. So I'm guessing that is continuous. 14x plus 3y equals 9. 9x minus 2y equals 49. Oh, no, okay. That does not what that mean. Okay. And negative 7x minus 6y equals k. Okay, so they all have the same solution. Alright, that works. So let's find the solution for the first two. That's really annoying with that, but whatever, it's fine. 14x plus 3y is 9, and 9x minus 2y is 49. Multiply both equations, top by 2, bottom by 3. We can get rid of the y's. Is 28x, 27x, plus 6y minus 6y is equal to 9 times 2 is 18. 43 times 3 is 147. 28, 27 is 55. X is equal to 165. Good. That's a nice one. Better be. So x is 3. When x is 3, this is 27. Nope, 27 minus. Right, second equation here. 27 minus 2y is equal to 49. Swap sides. This is going to be 27 minus 49 is equal to 2y. So y equals 27 minus 49 is negative 22 over 2. So negative 11. Okay, so solution will exist at 3, negative 11. And then we need to make sure that the other one also has that. So, negative 7, well, okay. Negative 7, negative 6, k. Negative 7 times 3, minus 6 times negative 11 is equal to k. So negative 21 plus 66 is equal to k. Negative 21 is going to be 45. Well, that's going to be interesting because that also does not work for a... That also does not work for a magic square. What y'all doing? Alright, how'd I mess this up? (14x plus 3y equals 9). Okay. 9x minus 2y is equal to, that was 49? Yeah, I think so. Solution 3, negative 11. Yep, cool. Okay, and then we say that this needs to be negative 7x minus 6y equals, right, if it's 2, it's up there. If it's 10, it's down further, and so we wanted this to be, what was it again? 45. Yep. 3, negative 11. And yet, let's try this again. So we've got (14x plus 3y equals 9). Eh. Not sure we need that kind of patriotism going on. Alright, let's also just double check the definition of concurrent to make sure I've actually got it right, because this wouldn't be the first time. Three or more lines that pass through a single point in a plane. Yep. (14x plus 3y equals 9). 9x minus 2y equals 49. Negative 7x minus 6y equals k. I mean, I don't need to split it up into something else. That's just what we got. Okay. Number 19 then. It's gonna be 45. wonder if this is something to do with Martin Gardner. Like, does he have something to do with 1945? Is that why this is different? Not really. Born October 21st, 1914. Died in May 22nd of 2010. Didn't really publish anything until, or like, you know, book-wise until 1952. Limes! Nice. Dare I ask which ending you went with? Was it the fast ending, the sit ending, or the nil ending? Yeah, you only have a limited amount of time to make a choice. Yep. And yes, there is a choice. Yeah. So my first one, I was like, you know, F this, and I just, I clicked about as fast as I could, just because I was like, well, that's what we're doing, right? That's the whole point of the game, and I also did not realize that there was really a choice other than, you know, yes, clearly we're gonna have to end the loop. Surrender of Japan in 1945, but that wasn't really his thing. Served as a yeoman on USS Pope in the Atlantic. Used to write for the Humpty Dumpty magazine. Wrote features and stories for other children's magazines as well. Paper folding puzzles led to his first work at Scientific American. Interesting. So, like, no, there's nothing significant that I can tell between Martin Gardner and That's the other thing, is that you can't perfect day it on the first shot. It's not possible. Thank you, Shark. Hydrate.
Raiding party!
Hey, Raiders. How's it going? Welcome, everybody. If anybody doesn't know me, my name is Obi-Wan Pez. This is N-Simplex Pachinko. We are... Woo! Peach Tea? Pen? How's it going? Enigma? If you were not already following either the Two Eye Pie, Zach, or any of the rest of us, we have the now math-famous Enigma bot. It's going to tell you the list of Chads to be following so that we can help you out with any sort of math questions you might have. Day 9 for our real analysis class is now in the books. I know, right? We gotta look up terms in, like, what does it mean if we can set up a team or whatever. I don't know. Seems like responsibility. Anyway, we were working through the... Oh, okay, partner to get a team. Yep, alright, that makes sense. Someday. The NCTM, National Council of Teachers of Mathematics, Mathematics Teacher Magazine, September 2011. We've been working on the one-a-day math problem calendar and just trying to, like, blow through it, so... Yeah. Oh man, Enigma. Yep, and they are, like, highly encouraged, I'm sure, for teachers to use them just out in the real world, because, you know, it's kind of fun. It gets the students involved. All that good stuff. We've solved almost all of them. I need to verify these two here in red. I already know quite clearly that the solution along the edge here is Martin Gardner. It was like, what does it say? The instructions say that the remaining answers, i.e. that block, pay tribute to a master of recreational mathematics. And I was like, all right. I'll give you half a guess. Hey, I know it's Martin G.A., so... and then... And I mean, this is October 2011, so it was like a year after he died, so it makes sense that they would want to pay tribute. But I'm having a bit of a problem here, because... you can quite clearly see the 3x3 square that's in there is Marvin's Gardens. Is quite clearly a 3x3 magic square. Right? But the thing at the bottom... Oh. No. Here we go. Yeah. Answers form 2 magic squares, a 3x3, and 4x4 array. But I've got 19 and 45. Those don't fit a magic square. Now, in theory, it could just be a 4x4 magic square and not like the 4x4 magic square that is all the numbers 1 through 16 only. Of which I definitely know one exists, because I have, you know, not only looked the stuff up, but what's his face? Albrecht Dürer did his wood carving called Melancholia 1, which has a 4x4 magic square up in the corner. And yes, I've checked it. So the 19 and the 45 came from two problems that are... Oh, that's going to be bad. Here's one. So this said, find the value of k, k being that bad boy right there. Find the value of k such that these three lines are concurrent. So I said, okay, let's solve the first two. You know, 14x plus 3y equals 9, and 9x minus 2y equals 49. And I went and checked it, and I went online to Desmos and graphed it. And yes, the solution for this is 3, negative 11. And so plugging in 3, negative 11 into please check my work. into x and y here is going to get us negative 21 plus 66 is k, which is 45. And I verified this because on Desmos, plugging those three lines in gets us the concurrent point 3, negative 11. Right? So then Herg. Yeah, so I'm thinking there's something fishy here. That this may not, in fact, be the kind of magic square that I was looking for, or it's like something super secret that they were throwing out there and doing something really weird. Like, hey, it's not even a magic square, we were just lying to you. Now, I don't think that they would do that, but they could do it in the name of, like, wanting to do something cool. Again, I don't think that they would, just, you know. Alright, so now we're getting into uncharted territory here. Let's see. That's 19. 18 was find. Is this it? No, it's 13. It's way bigger. That was bad. Okay, I meant to zoom out. There we go. 18 is over here. This one was given this quartic function here, or expression, we need to separate it into two unfactorable quadratics that have integer coefficients. Mod 16? Maybe. They didn't specify, but you know. That's going to be 3. And 16 is going to be negative 3. It's going to be 13. All right, 15, 14, 13. Yeah. Okay, so that's 13 and 3. 13 and 3 is 16. Plus 15 is 31, which I don't think is correct for a 4x4 magic square either. I'm pretty sure it's 34 is the correct value. But hey, it's a lot closer. Yeah, either that or something just much trickier. So anyway, we looked at this one over here. We said this is unfactorable quadratic functions that come out of our quartic function. Again, A, B, C, D, E, F as our coefficients. A and D have to be 1 because they're integral coefficients, and the coefficient of x to the fourth is 1. So that's there. We said that if you multiply all this stuff out, we get E plus B is our cubic term. F plus BE plus C is our quadratic term. BF plus CE is our linear, and C times F is our constant. So CF needs to be negative 7. Without loss of generality, just plug something in and hope. At this point, we do have to, there is a loss of generality at plugging in positive 7 and negative 1, but I figured most of the stuff's positive, so let the bigger number be positive. And then try to look for values that we're going to work for. B plus E is 11, that one right there. And I tried out 6 and 5 first, reversed them, and then realized that we needed the bigger number to be E, so we can multiply by 7 here and get 53 here. So 7 times 8 is 56, and then 3 times negative 1 gets us that negative 3 to knock it down from 56 to 53x. And then verified all the rest of it that, yeah, that works. But then when we add up all the coefficients, you get 19. Like Like, unless I really mess something up here. I may have. No, I counted it. Okay. Yeah, the 7 times the 1x squared and the negative 1 times the negative 1x squared gets you 7x squared minus 1x squared. And then this is the quadratic is the 3 by the 8 linears to get you 24x squared to get you 30x squared total. Okay, anyway. So yeah, I don't know where this is going. But hey, I'm in it to figure out what the matter is. Because, like, that's not supposed to happen. Alright, so number 20 is a geometric diagram. We have a rectangle. ABCD. D. With N and M. Midpoint of AB is M. So we got those two sides there. DN. It's connected NM and DM, which are all straight lines. Definitely. N is going to be 1/3 the distance. So we're going to go 1, 2, 1, 2, 1, 2, like that. Compute the area of D and M. Yep, I mean, that's me too. Oh, I did get a very nice pen. This was almost a year ago now, from one of my students last year. It was a Tornado pen, which has mathematical, or calculus. It has calculus just written all over it. I'm thinking it might be relativity, but but he was just like, look, I'm really appreciative, you know, and all this stuff. I was like, I really don't accept presents, but oh, that's nice. He wasn't my student anymore, so it's fine. And like, it wasn't, you know, money or something that would be really awkward. It was like, it is a pen, a nice pen, but not like, you know, certainly not $100 or something like that. That would be like way too much. Yeah, it definitely makes sense. And it was like, yeah, it's perfect because it's got math all over it. Yep. At some point, I asked he was the associate dean for a while. He's now just, or was one of my colleagues, you know, up until last week when I left the job. But he stepped down from that particular position because they did another search. And yeah, I ended up, I was tutoring a student from somebody else, like one of my other colleague students, and she came over to my room and asked me all sorts of questions, and I was like, yeah, sure, fine. Like, I've got nobody here. You might as well, you know, come in from my office hours. I don't care. So we developed a nice little, you know, student-teacher relationship, whatever. And she was like, look, I'm really appreciative of everything you've done, and you've, like, volunteered your time to help me, so I wanted to get you something. And I was like, that's kind of nice. I'm a little sketched out. And it was a watch. And I was like, yikes. Which, granted, had it not been against my contract to, like, charge money, if she were a private tutoring student, it would have cost like hundreds, if not thousands of dollars to get where, you know, to get that whole thing done by the end, or to get where she was at the end of the semester. So I was like, that's a little sketchy. So I went over to, you know, our assistant dean's office, and I was like, look, this person is giving me like I didn't look it up at the time, but I looked it up afterward, and it was like $250 watch, and I was like, she's giving me kind of a nice watch. I'm thinking it was from her work, and like she got an employee discount or whatever, or it fell off the back of a truck somewhere, and you know, it wasn't available. It wasn't supposed to be sold on the floor. So like, you know, you take defective items home. So I mean, she could have gotten it for really cheap or free, and given me this thing, and I was like, and yeah, the other guy was like, he said, so is she your student? And I was like, no. And he says, okay, it's fine. I'm not sure I agree, but all right. I did, yeah, eventually. I said thank you. I was very gracious, and I was like, I'm not sure how I feel about it, but you know, thank you very much. And she was like, oh, okay. And then again, the associate dean was just like, yeah, it's fine. It's not your student. What does it matter? It's like, okay. So I thought that it was a rule in our contract that we were not allowed to accept payment for, you know, math services, teaching math, to any student from our college. Like, that was my understanding of the rule, and that it was against our contract if you did. So, right, and that's a question, right? Is gift payment? I think it would be like, if it was commensurate to the amount of money you would have spent, then yeah, probably. But in this case, right, it was a simple token of appreciation or whatever that was a fraction of what she probably would have. And it wasn't like I was that's fair also. Students buy you wine all the time. Oh my god. Oh my god, I'd have so much scotch right now, it'd be ridiculous. Oh, yeah. Okay, that's true. It's easy to come by here too, but you wouldn't want it. It was interesting. When I was up in New Hampshire, they had, oh, whoops. Nope. That's just BC over 3, not... Did you tell him hard liquor was off limits? Yes. Agreed. Jamaican rum is excellent. Okay. Area of the rectangle. There we go. 48 square units. Right, and then we want the area of the triangle. Well, okay, fine. DMN. You know I gotta do it. Getting a little punchy. Okay. Clearly must be bedtime. Alright. So this is going to be 1/2 times 1/3 BC times CD is the same as AB because it's a rectangle. Okay, and then this is going to be 48 minus that area plus area of B and M, which is going to be the 2/3 BC. Oh, damn. Okay, 1/2 times 2/3 BC times 1/2 AB. Okay, plus this one is 1/2 times 1/2 AB times AD is the same as BC. Okay, and that's the area of DMN. Admin. Alright, so this is going to be 48 minus parentheses. This is 1/2 times 1/3 is 1/6 of AB times BC. That looks suspiciously like area of the rectangle. So that's 48. You wonder why I did this, huh? Plus 1/2 of 2/3 is 1/3, and 1/2 of 1/3 is 1/6. Times BC times AB, again 48. That cleans up very nicely. 1/2 of 1/2 is 1/4 of ABBC. So 48 minus. Factor out 48 from all of it. No, I guess not. It's fine. 1/6 of 48 is going to be 8, and 8 again, and 12. So that's minus 28 leaves 20. Yeah, there's something going on. And like, maybe I'm just paranoid or whatever, but... All right. $21. Uh-oh. What's the matter, Excalibur? Are we filling up? In 1941, Fred's children were both between the ages of 10 and 20. 1941. Fred's children. Man. Hang on. This is going to be fun. So, they were between 10 and 20. So, 10 less than Fred 2, less than Fred 1, less than 20. Sum of the cube of one child's age and the square of the other child's age gives the year in which Fred's wife was born. Oh, man. Sum of cube of one child's age. It's not going to tell me either. Oh, no. F sub I squared plus F sub J cubed is going to be equal to the year of Fred's wife. Find Fred's wife's age in 1941. dirty. That is a dirty trick. I mean, look, if Fred or anybody else in his family is as good a mathematician as Srinivasa Ramanujan, then it would be just instantaneous in order to be able to figure out, right? Oh yeah, well, the year in which you were born is the sum of the square and cube of our ages. Oh man. Okay, so I'm going to assume here. Now, maybe this is a big assumption, but I'm going to assume that Fred's wife is going to be at least greater than or equal to 18 plus the age of the first child. Might be a stretch, but at the same time, this is supposed to be a family-friendly magazine, so, you know, just going out there. So, yep, that's true. Oh, between, okay, let's, colloquially, it may also be, yeah, could potentially be equal to, I suppose. Right, they're not both going to be 10. Because that would be 1100. So, it should be 800 years old. I don't think so. Just, you know, probably. And to put a lower bound on that, or upper bound on it, she probably was not 60. Let's just argue that. Alright, let's flip this around. Alright, like I said, I'm making an assumption here, but I'm gonna guess probably. I'm gonna make a big assumption. Again, doesn't have to be true, but let's focus inward on that and then worry about it as we go out. So putting a bound on it, this is going to be in 1941. If she is less than 60, that would mean she was probably 1881, right? Yeah. Year. Oh, that'd be the lower. And she would be at least 28 years old. So let's go with 19. What, 13? Yes. So, again, assumption, but we're going to just kind of narrow in on this and assume that this is probably where the kids are, or this is where she likely was born, and then we'll move out from there if we have to. Nope. This way. Let's not do that. Okay. So, if we go with year, nope, age. And then AH squared and AH cubed. Right, we only have to do 10 through 20. These are the worst ones to do. Hey, I may actually owe somebody something here. Hang on. Hey. Did I just talk through a break at some point? Because I feel like I haven't done ads in a bit. It's probably coming. Okay, squares are going to be 100, 121, 144, 169, 180, nope, 96, 225, 256, 289, that's where that one came from. That's where I crap out, 400. Alright, 18 squared is going to be 164 and 160, 324. And 19 is going to be 181 and 180, so 361. Right? Let's see. That's going to be 37, and that's going to be 39. Yep. Okay. All right, this is 1,000. 11 cubed. Oh, right. 1331. I should know that. 12 cubed. Right. This is going to be fun. Okay. I need to stop worrying about this because it's literally in front of me. This is the pachinko thing that I've been doing forever. Okay, so 1331 is going to be 1,000. So 3 of those is going to be 300. That's not it. Hang on. Right, 3 2s times... No, that's not it either. Damn. Okay, there are 3 things. We do either the 1 cubed is getting us 1,000. The 1 squared times 1 2 is going to get us a 2. Why is this not working right in my head? Right, but times 3. Okay, so 6. Jeez. Okay. Then 3 2s. Sorry. Okay. So the Pascal triangle. Oh, hang on. Nope. No, no, no. Nope. Oy. A plus b cubed is going to get us 1a cubed b to the 0 plus 3a squared b to the first plus 3a to the first b squared plus 1a to the 0 b cubed. Ew. Right. So in this particular case, right? So 1,000. Silver! How's it going? 3a squared is again 100 times a 2. So 200 makes it 600. Then over here, this is going to be 4. 40 times 3 is 120. So 7. $20. And lastly, it's just, did I even do that right? 4 times the, yeah. And lastly, that's 2 cubed is just 8. So yeah, 28, 1728. I should have known that one, because that's the taxi cab number. God damn it. No, I did 10 and 2, which, I don't know, 6 and 6 might have been easier. So my habit is usually just break it into literally what you see. So 10 and 3 is, yeah. 10 and 3 is going to be, again, 1,000. And quite possibly it's going to go beyond 1,000, but whatever, it's fine. And then here we get hundreds times 3. Times 3 again is 9, so 900. It's going to be 9 times 9 again is 270. So 2170. And then 3 cubed is 27, so that's 90, 2197. Yeah. The other thing we could do is look at the pattern that we have between them. So this is plus 331. This is plus 380, 97. This is 400, 469. Which then if we also look at the, you're going to hate this. Look at the pattern between those. This is going to be add 66. This is add, really? 72. This is plus 6. This is cube, quadratic, linear, cube, quadratic, linear, constant. So the next one should also be a plus 6, which should be a plus 78, which should be a plus 547. Which is going to get us a 27. Having a rough day, it's fine. 44. Let's check that really quick to make sure I did all the rest of them right. All right, 14 times equals 2744. Cool. This I figured out in, I think, 6th grade. Without any prompting. I was just like, that's a really weird thing. Like, I think our teacher gave us a quadratic, and it was just one of those, it was just a table, and it was like, hey, find out what the next number is. And I was like, I don't know, but it's kind of interesting. You know, I had gone through all the linear examples as being like, oh, look, this is +1, etc. And on like another one, it was, oh, it's plus 6, plus 6, plus 6. Okay, cool. And then when I did this in, you know, for the quadratic example, I went, okay, what is 100 to 121? It's plus 21. Well, it's 121 to 144. Well, it's plus 23. And then the next one's 25 and 27. And I was like, well, that's a linear pattern. So what's the difference between those? And I went there. Yeah, I mean, it was, yeah. like I said, I was in 6th grade and I didn't know algebra. So, like, sure, why not? And I went for it. And everybody's like, how did you do this? Like, you got it so much faster than we did. I was like, yeah, because you just do this thing instead. Right, and then the other option is we already got the squares, so multiply them by the other number that's over there. So like 225. I could do this one probably in my head, but ew. Um, oh, anybody who's interested, Vedic math, the way that it's taught in the Hindu Vedas, is how do you get ones? You multiply ones by ones. So 5 times 5 gets you 25. You carry by putting down. How do you get tens place? It's tens by ones and ones by tens. Tens by ones, tens by ones, whatever. It's 2 times 5 plus 1 times 5 is going to get us 15, plus the 2 that we carried over is going to be 17. How do you get the hundreds place? Well, it's going to be tens by tens. Oh, foul. It's going to be tens by tens, but it's also going to be hundreds by ones, and ones by hundreds, we just have a 0 here, so that doesn't show up. But for that, again, that's going to be 2 times 5 is 10, plus 2 times 1 is 2, so that's 12, plus the 1 from the bottom is 13. How do you get the thousands place? Well, that's hundreds by tens, which is the last thing we have. 2 by 1 is 2, plus the 1 underneath is 3. So 33, 75. Yeah, so the Hindu Vedas, I mean, allegedly, I haven't looked into it myself, but I trust Alex Bellos that he did, in fact, look into it. He took a trip to India to, like, you know, check out the cool stuff. Bit like Marcus de Soto, honestly. And he wrote his book in England. It's called Alex's Adventures in Numberland. And in America, it's called Here's Looking at Euclid. Both plays on, you know, famous famous phrases from, respectively, Alice in Wonderland and Alice's Adventures in Wonderland. And, well, he got paid to do it, so, you know. And Casablanca. All right, so 256 times 16 is going to be increased by power of 4. So it's already 2 to the 8th. That's going to be 2 to the 12th, which is 2048, 4096. And 8,000 here. Right? I mean, realistically, we don't need any of this stuff at all. Oh, hang on. We don't need any of this stuff at all anyway, because, you know, 1728 is going to be the hard ceiling on this one. If she's going to be born prior to 1913, we suspect. Yeah. Yeah, well, Khan Academy math in other languages, like, will help you understand the language, but at the same time, it's not going to help you, like, get the... I assume that's not going to get you, like, their method. Like, if you went to Singapore right? They teach the Singapore math method. It's nothing. I won't say it's nothing like the American version, but yeah. So I mean, it should be Sal's video that's been dubbed over? Question mark. Okay, so candidates. I think 196 plus 1728 seems reasonable. Now, I said probably prior to 1913. This is going to put her at 1924. Which 24 to 41 is 17 years. Which, again, possible. $17.28 plus 196 is equal to 1924. Oh, that puts her at 17 years old now. Yeah, that's really sketchy. That's not going to happen. No, screw you. No. If the kids are between 10 and 20 and she's 17, that's not happening. Nope, F it. Alright, what about 169 and 1728? That's going to be 1897. That looks much better. 1728 plus 169. It's going to be, again, 8. Oh, jerks. All right, 1897. Going to 1941 is going to be 44 years. Ooh. Yeah. Come on now. Wake up. Wake up. Come on board. Alright, I'm going to accept that one. So, 44 years old. Sounds good to me. I suppose it could also be the sum of the digits that gives you the proper entry into here. Again, all numbers 1 through 16 should allegedly be used if it is in fact a magic square. 44. Enigma. Alright, got a nice little space up here. This is going to be... 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Right? Cool. Yeah. Compute the maximum value for the following function. F of x is equal to 3 sine of 3x plus 4 cosine of 3x. So f prime of x equals 0. It's going to get us the maximum for this particular function. This is going to be 9, cosine of 3x minus 12 sine of 3x. Maximum value. So we can get the x value, but then we need to plug it back into the original function. So this is going to be 12 sine of 3x is equal to 9 cosine of 3x. And at this point, I would probably want to bring this over, and make it the tangent of 3x is equal to 9/12, which is equal to 3/4. So when do we get a value of 3/4? It's a 3, 4, 5 triangle. That's all we need. Yeah, because our sine and cosine, we know what it is. Right? This is going to be a 3, 4, 5 right triangle. And so if the original sine is going to be 3 times 3/5 plus 4 times the cosine is 4/5 is going to be 9 plus 16 is 25 over 5. Nice. Is just 5. It's like I'm not going to question that one, right? Actual number makes sense. Okay, 23. Only a few more to go. Woo! Perimeter of a sector of a circle is 40. So this is going to be r, and r theta. S equals r theta. So that's going to be 2r plus r theta. It's going to be equal to 40. Find the radius of the sector that maximizes its area. Oh, that's a dirty trick. Area of a sector is equal to 1/2 r squared theta. One half r squared theta. All right, cool. I know that. What? I've only been teaching it for friggin' ever. All right, so we want to maximize, which means that we're going to get a prime is equal to 0 is equal to, bring the 2 down, that knocks out the half, so r theta. All right, that's not funny. No, that doesn't work. Sorry. That is plus 1/2 r squared. Hang on. No. Mm-mm. Move that over. Because that's also times dr d theta. We're doing this in terms of theta. Okay. plus 1/2 r squared. And that's d theta, so that's gone. This is also one of the reasons that I recommend and advocate for the use of the general derivative operator. So rather than a prime, this would be dA is equal to r times theta times dr, plus this would have been 1/2 r squared d theta. And then you could choose which one you want to take with respect to, and nobody's going to care. Because they're all going to be correct. It's just a matter of making sure you're getting things straightened out. Okay, so dr d theta, that maximizes all this stuff. We're going to get 1/2 r squared divided by r theta. So one of the r's goes away. Yep, so I use the general derivative operator. It's much easier to work with in terms of like, oh no, I don't remember all the ridiculous rules, and like, when do I make it in terms of this, and when do I make it in terms of that? Like, who cares? We can just turn everything into a derivative. And you say, like, I'm taking the derivative of A, so it becomes dA. If at a later time I would like dA dr instead of dA d theta, I can make that choice and divide through by the appropriate differential. If I want d theta dA, I could do that. Right? I don't know why you'd want to, but whatever. It's cool. This also makes it much easier to work with in terms of differential equations, because when eventually you want to separate your variables, you're going to say, okay, I'm going to separate my variables, so I'm going to get all of my like A stuff over here, and I'm going to get all my R stuff over here. Then you've got your separation of variables. You can take the integral of both sides, and now you don't have to worry about like, do I have the appropriate, terms or anything like that. It's all going to just be individual differentials. Again, dA, dr, and d theta. And then you definitely know what you're taking your integral with respect to. You don't have to think about it. All right, that's a negative r over 2 theta. Which is really interesting because that's definitely how we prove the chain rule. Because when you talk about the chain rule, we say like, okay, I want ddx of f of g of h of j of x. 1, 2, 3, 4. Okay, wait. 1, 2, 3, 4, 5, 4, 3, 2, 1, 0. Okay. When you're taking the derivative of this stuff, you're saying, okay, I want to take the derivative with respect to x of this immensely compound function. And you say, okay, well, I can't take the derivative of f with respect to x because it's not written that way. F is not in terms of x. So you say, okay, what is f in terms of? F is in terms of g. So this is ddx. We can multiply by a dg over dg. And then we end up doing dg of f of g of h of j of x. And then we've got this little bit on the outside, which is now a dg dx. Like, this is how we show the chain rule. So they are fractions, to a point. Like you can mix your differentials and like the operators and stuff like that. That works sort of okay. And maybe they don't want you to do that either, but whatever, it's fine. All right, and then we would just repeat this whole process. So this is going to be df dg, right? And then we got to do dg dx, but we can't do dg dx because again, g is not in terms of x. So then we have to go one further and say that we're going to have to do, okay, well, this is going to have to be dh. So now this is going to be ddh of g of h of j of x times dg dh times dh dx. But when you think about it, I think I went one too far here. No, that's okay. That works. Oops. No, not yet. That's the problem. Can't do that one yet. And then here's the original chain rule, right? That dj of h of j of x is going to be, or is going to then be multiplied by dj dx, the derivative of the inside of that stuff. All right, anyway. The perimeter. Perimeter's 40. Did I go one too far here? Like, we could take the derivative of the perimeter, but I don't think it does really anything for us other than finding some sort of relationship between drd theta and the other two variables. I don't think it's very productive, but R is a constant. That's fun. No, but if I do that, then R is going to be equal to 0, so that doesn't make any sense. Right, R... Find the radius of the sector that maximizes its area. Well, okay, so actually, right, R and theta can both be variables. That's fine. Because then we're just making sure that, like, we're changing where the 40 is going to be put. Is it going to be put more on the radii, or is it going to be put more on the angular side? On the arc part of the circle, or sector. That's okay. So actually, maybe our perimeter function can be derived and makes it a little bit easier? Question mark. If we do this, this is going to be 2 dr d theta plus dr d theta plus r is equal to 0. Okay, dr d theta. Dr d theta is going to be equal to, this is going to be 2 plus theta on the denominator and a negative r up here. Okay, that's perhaps a little confusing. According to these two equations, that should now mean that 2 plus theta is equal to 2 theta. So therefore, that implies that theta is 2. Uh-huh. So 2 radians. Not sure I believe it, but alright. Which is going to mean that 40 being our perimeter is going to be 2r plus r times 2 is equal to 40. Alright, cool. 4r equals 40, r equals 10. Find the radius of the circle that maximizes its area. Yeah, I guess. It fits the question. We don't have a 10 yet, so that's, yeah, it's possible. I wonder. Maximize area of circular sector whose perimeter is 40. Does putting articles in help? No. Right, the radius is going to be 40 over 2 plus theta. We said theta was 2, so it gets us 4 in the denominator, makes it 10. Cool. Area is going to be 800 theta, so 1600, divided by 4 squared is 16, so 100. Okay. 40 theta is going to be 80, divided by 4, right? It's going to be 20, and then 10 each for the other radii. Okay. Okay, area. So 800x over x plus 2 parentheses squared. Okay. Ooh, there we go. Nailed it. 2, 100. All right. Worked pretty well. All right. Mm-mm. 24. I think we're down to our last couple here just because my headphones are running out of battery and it's almost 1 o'clock, so, you know. But I think tonight we're probably going to go see Mahoodles if nobody else is on. Thought she was supposed to be on. No? You're not doing the thing? Okay. Well, I guess Mahoodles is not on tonight. Balint is on doing science, doing Tinker Tuesday. So they're making a submarine? Maybe something else? Alright. So, last one. And then we'll, I think, go right over to Balint. He and his wife Lita are doing some sort of, looks like maybe a model. Alright, teacher bought 100 puzzles for $82.90 to give out to the members of the math team. She bought 3 different types of puzzle. Type A, okay, total. Type A, B, and C. The number of each sums up to 100. Or, yeah, whatever. You know what I mean. The cost of each one. A costs 40 cents, so 0.4A. Plus B costs 70 cents, 0.7B. Plus type C cost $1 each, so just that. That gets us $82.90. How many more type C than type A did she buy? So, how many more of type C than type A? So C minus A is going to be our objective. And that could be our, I don't know, magic square, D. Alright, so do we want to get rid of B? I think so. So we'll do negative 0.7. negative 0.7a. Huh. Minus 0.7b minus 0.7c is going to be equal to negative 70. Okay, 0.4a plus 0.7b plus 1c is going to be equal to 82.90. 0.3c minus 0.3a is equal to 1290, which also means then that this is going to be c minus a times 0.3 is equal to 1290. So c minus a is going to be equal to 1290 over 0.3, which is 129 over 3, which is going to be 43. Alright, I lied. Ant on the outside of a glass 3 inches from the bottom sees a drop of honey inside the glass 5 inches from the top and exactly halfway around the glass. The glass is 13 inches high and has a circumference of 16 inches. Compute the length of the shortest path for the ant to reach the honey. Okay, that one's pretty cool. Okay, so ant. Alright, if we're going to raid Berlin, we need to do this, right? So this distance is going to be 3 inches. Inside and opposite. Opposing position. All right, 5 inches there. So we want to draw a straight line, but we can't. So this is effectively, I think, going to be something like this. It goes like straight up to the top and then kind of curves around the glass like that. And like, while it's on this side of the glass, it's also like, it's also curving, but it's going to be less easy to see just from something like that, give or take. Okay, that's going to be pretty challenging to figure out. If anybody wants to give it a shot, feel free, and we will... Oh, right, the whole glass. Jeez. Is 13 inches high and has a circumference of 16 inches. So this ought to be nice and hard to figure out, or there's some like easier way to do it. But either way, if we were to flatten it all out, right, this is still going to be a straight line. It's just going to be more interesting because this is on a curved surface. All right, let's go read Balint so we can go talk ants. Commiserate over the fact that we had ants in a problem. Alrighty. I hope everybody has a wonderful evening. We'll see you on Thursday on Zach's channel, E to the 2i Pi, for Real Analysis, which I am part of that class. And then we'll also get Game Night on Friday. We're doing code names with the Elements crew. So a whole bunch of us are getting together to play code names. If you don't know what it is, stay tuned to this channel, because I will be happy to do that. Or one of the other Chads, if you will. Feel free to head on over to one of theirs on Friday night, 9 p.m. Sorry, 9 p.m. Eastern. Oh, man. That's 0200 UTC Saturday morning, technically, but you know what I mean. Hope you all have a lovely rest of your week, and we're going to go ahead on over and see some more science people. Have a good night, everybody. This is Obi-Wan Pez for N Simplex Pachinko.